Imagine you're sitting at a really nice restaurant with a big group of friends. You've had a great meal, lots of conversation.
Yeah, good times.
Right. And then the waiter drops the check on the table. You casually glance down at the bottom line, and the total is just wildly different from the sum of everything you all ordered.
Oh, I hate when that happens.
It's the worst. So you start going down the list. Burger, check. Salad, check. 3 coffees, check.
Right.
You add up the individual items, and the sum just does not match that massive number staring back at you at the bottom of the receipt. I mean, someone's math is completely wrong, or there was something completely invisible hiding on that bill.
It's a really jarring disconnect, You instantly know there's a fundamental rationality failure in the transaction right there. The math either works or it doesn't.
Exactly. And today, we are taking that exact, highly frustrating scenario and translating it into the world of electric vehicles.
Because in the multi-billion-dollar world of high-voltage battery management, that invisible math error isn't just an annoyance over dinner.
No, it's not. It is a critical system-level rationality fault. In the engineering world, it has a specific designation, right?
Yeah, it's known as the P0A03 pack voltage mismatch error.
And we really need to establish the stakes here right from the start for everyone listening.
We do. This is not a tiny software glitch. I mean, this isn't a faulty Bluetooth connection or your screen freezing up for a second.
Right.
In the Automotive Functional Safety Standard, which is ISO 26262, this is classified as an ASIL-D level safety issue.
ASIL-D, that's Automotive Safety Integrity Level D, right? The absolute highest classification of risk.
Exactly. If this voltage sensing blind spot is mishandled by the vehicle's computers, well, the resulting actions could leave a driver totally stranded on the highway.
Like at highway speeds without steering assist?
Yeah, or it could lead to catastrophic hardware failure, like literally melting the main power switches of the car into a permanently closed live state.
Wow. Okay, let's unpack this. Our mission for this deep dive is to completely deconstruct this invisible threat. We want to understand this on a molecular, hardware, and software level.
Sounds like a plan.
We're going to start by tracking down the root cause of this phantom voltage. Then look at how the car's architecture attempts to cross-check the math.
Right.
And then get into the incredibly aggressive design and manufacturing measures engineers use to eradicate the problem before a car ever hits the road. We'll end by looking at the absolute torture chamber they put these batteries through to prove they are safe.
It's basically an invisible war of precision happening right under the floorboards.
Yeah. So to grasp the P0A03 error, we really have to look at the fundamental architecture of the sensing systems.
Exactly. We are talking about a scenario where the total pack voltage, which is measured by an independent high-voltage sensor, suddenly refuses to match the sum of the individual cell voltages.
And those individual cells are being pulled by the analog front-end chips, right? The AFEs.
Yeah.
The AFEs. Okay, let's start with the physical electrical pathology. Like, what is mechanically going wrong with the hardware to cause this mismatch?
Well, let's look at the phenomenon of high current parasitic drops.
Right. So if you slam on the accelerator to merge onto the highway, or maybe you hit the brakes hard to trigger regenerative braking, you're commanding hundreds of amps of current.
Yeah, you're dealing with extreme dynamic loads. All that current, sometimes like 400 or 500 amps, is surging through the high voltage bus bars.
Those are the thick copper plates connecting the battery modules in series, right?
You got it. And it's also routing through the main contactor relays, the pre-charged circuits, and the high-voltage fuses.
Okay.
The issue arises when the physical integrity of those pathways is even slightly compromised.
Compromised how? Like just a loose bolt?
That's one possibility, yeah. But it goes way deeper than just torque. Think about the thermal cycling a vehicle goes through over years of operation.
Right, like extreme heat during fast charging and then freezing temperatures in winter.
Exactly. This causes microexpansions and contractions in the copper and the steel bolts.
Oh, I see.
And over time, the surface plating on those copper bus bars can begin to degrade. That allows microscopic oxidation layers to form right between the contact plates.
So you basically have a microscopic layer of tarnish trapped between two massive copper plates that are supposed to be flawlessly conductive.
Yeah, perfectly put. And in electrical engineering terms, that tarnish, or that microscopic loss of clamping force, introduces a million-level parasitic resistance.
A million. So we're talking about incredibly minute resistance values. I mean, why does a fraction of an ohm matter on a battery pack pushing 400 or 800 volts.
It comes down to Ohm's law acting dynamically under extreme load. I mean, the resistance might be tiny, say 5 milliamps across a specific connection point, but you have to multiply that by the current to find the voltage drop.
Right, Ohm's law, current times resistance.
Exactly. So if you floor the accelerator and pull 400 amps through a 5 milliamp parasitic resistance, you instantly generate a 2-volt drop across that single physical joint.
Wow, 2 volts lost on just one joint. And a typical battery pack has, what, dozens of these connections?
Easily dozens. So if you have several of these microscopic imperfections compounding across the entire series string under a heavy dynamic load, well, you're suddenly looking at a massive multi-volt dynamic trot.
Wait, so the car thinks it's losing voltage, but it's really just hiding in a rusty bolt? The total energy in the battery hasn't actually disappeared?
That's the physical reality, yeah. It's just being temporarily burned as heat across these oxidized joints during acceleration.
Oh, wow.
But here's why it triggers the P0A03 rationality fault. The vehicle relies on 2 separate vantage points.
Okay.
The total pack voltage sensor sits at the extreme ends of the entire circuit. It looks at the macro picture, so it actually captures that multi-volt drop caused by the bus bars and the bolts. It registers a sudden dip in available voltage.
But the individual cell sensors, the AFEs, those are mounted directly on the cells themselves.
Correct. The AFEs are only measuring the localized chemical voltage of the individual cells. They completely bypass the thick copper bus bars, the relays, and the bolts.
So the total pack sensor says, hey, I'm only seeing 390 volts. But the AFEs look at the cells and say, wait, we add up to 400 volts.
Exactly. The math on the restaurant receipt doesn't match because the massive gratuity fee of the oxidized bolts wasn't included on the itemized list.
That is wild. The total sensor sees the macro-level failing hardware, while the cell sensors only see their own isolated, idealized chemical states.
Yeah, that captures the discrepancy perfectly.
But there's a second pathology here, right? And it doesn't even rely on physical degradation. It's a signal and protocol issue, something about timestamp mismatches.
Right. This is where the sheer speed of electricity outpaces the microprocessors. Inside the battery management system, you essentially have 2 entirely different sensing architectures operating simultaneously.
Okay, lay it out for us.
The AFE chips, the ones measuring the individual cells, they operate on a sequential polling mechanism.
So they're querying the voltage of the cells in a sequence, one after another, moving down the line, like roll call.
Exactly like a roll call. They use multiplexers to switch from cell to cell. It takes physical time to switch, read, and convert each analog voltage to a digital signal.
Makes sense.
But meanwhile, the independent high-voltage sensor measuring the total pack voltage is using a completely separate, dedicated, high-speed analog-to-digital conversion path. It samples the entire macro voltage instantaneously.
Because these are 2 different hardware pathways with different conversion methods, there has to be a timing discrepancy. Like, how big of a gap are we talking about?
At the microprocessor level, this delay is typically between 10 to 50 milliseconds, sometimes higher, actually, depending on the CAN bus traffic and the specific architecture of the internal communication network.
Okay, 50 milliseconds. I mean, in the grand scheme of human perception, that's virtually instantaneous. Why is a 50 millisecond delay triggering an ACLD critical safety fault?
Because of a parameter known as DIT. That's the rate of change of current over time.
Oh, right.
Imagine that extreme dynamic load again. You stomp on the accelerator pedal. The motor inverter demands a massive influx of current instantly. The total pack voltage sensor, with its dedicated high-speed path, captures the resulting heavy voltage drop in real time.
But the cell sensors are still sequentially pulling down the line. They are 50 milliseconds behind the physical reality.
Precisely. For that 50 millisecond window, the total sensor is reporting a heavily loaded lower voltage, while the sum of the cells is based on data from 50 milliseconds ago, when the vehicle was just coasting and the voltage was high.
So the system is comparing 2 different moments in time and assuming the battery is fundamentally broken.
Yeah.
It's basically a phantom transient mismatch created entirely by lag.
And this discrepancy can be several volts wide. The software algorithm looks at the difference, sees it violates the safety threshold, and just assumes a catastrophic internal short or measurement failure is occurring.
It's like taking a panoramic photo on your phone while a car drives by.
Oh, that's a good analogy.
Yeah, the background is fine, but the car is stretched out and distorted because the camera couldn't capture the whole scene at the exact same microsecond. The hardware is creating a false reality based on bad timing.
That's a really solid way to visualize it. But beyond parasitic resistance and signal latency, there is a third root cause we need to analyze.
Right.
Actual hardware faults and configuration errors, specifically something known as sensor drift.
Okay, this relates to the extreme operating temperatures inside the high voltage distribution box, right?
Yes, exactly. Inside that box, you have main contactor relays snapping shut, high voltage fuses, and thick copper routes carrying all those hundreds of amps. These components generate immense localized heat.
I can imagine.
And sitting right next to these screaming hot components on the printed circuit board are the total voltage sensing circuits.
Now wait, I want to dig into how those sensors actually work.
Yeah.
You can't just pipe 800 volts of raw power directly into a fragile silicon microchip to measure it, right? You could just explode.
You absolutely cannot. The analog to digital converters on those chips can only handle about 3 to 5 volts.
So how do they do it?
Well, the engineers use a series of mega-ohm divider resistors to step that massive 800-volt potential down to a safe, readable level.
So a mega ohm resistor is basically providing a massive amount of electrical friction to drop the voltage.
Exactly. But these resistors are precision components. Their accuracy is highly dependent on their material properties, often a specific carbon or metal oxide film.
Okay.
If you constantly bake these resistors next to a 90°C relay year after year, you induce thermal degradation in the resistor's crystalline structure. It's a permanent, irreversible aging process.
Wow, so a resistor that was perfectly calibrated to be exactly 1 million ohms out of the factory slowly morphs into, say, 1.1 million ohms over time.
And that is sensor drift. The physical resistance drifts by 10% or more. Because the resistance value fundamentally changes, the step-down voltage it feeds to the microchip also changes.
So the total pack voltage sensor is now permanently lying to the vehicle's central processor.
Yeah. But what about the software side of this? The source material mentions profile mismatches.
Right. This is a configuration rationality error. Imagine a physical battery pack architecture that consists of exactly 96 cells wired in series.
Okay.
But during the manufacturing process, when the battery management system's firmware is flashed, the parameter data set injected into the logic board accidentally configures the software to expect 100 cells.
Oh, I see. So the software logic is summing up the voltage of 96 physical cells, but it's attempting to compare that sum against an expected total voltage profile of 100 cells.
Right.
The math is mathematically boomed from the moment the car boots up.
Exactly. Or consider a physical failure on the AFE itself. The system is correctly configured for 96 cells. The physical box has 96 cells, but a single channel on one of the multiplexers burns out.
Right.
The chip simply skips that cell and reports the sum of 95 cells.
In all these scenarios, whether it's the wrong software profile, a thermally baked resistor, a 50 millisecond latency gap, or microscopic oxidation on a bolt, the end result is identical.
The total voltage does not equal the sum of the parts.
And that presents a massive diagnostic challenge for the vehicle's architecture.
So we have phantom voltage hiding in hot bolts, sensors that are literally taking photos out of sync, and hardware baking itself into inaccuracy. How on earth does the car's brain figure out what's real and what's fake?
Well, that perfectly transitions us into the technical architecture and fail-safe diagnostics.
Right, the brain's the operation. Yeah. How do engineers build a system that can cross-check these voltages, deduce if the error is real or just a transient ghost, and safely manage the vehicle without causing a catastrophic accident?
The foundation of this system is dual independent asymmetric sampling. It's a hardware-level redundancy mandate designed to totally eliminate single points of failure.
Asymmetric sampling. It sounds like they're intentionally building two completely different nervous systems to double-check the same organ.
That is precisely the design philosophy. You have two distinct pathways. Pathway A is managed by the master board. This board utilizes an isolated high-voltage operational amplifier, or an isolated ADC, to directly read the macro total pack voltage.
When you say isolated, how does an op-amp or an ADC achieve electrical isolation from the high-voltage bus it's measuring?
It typically uses galvanic isolation. This is often done via highly specialized optocouplers or capacitive isolation barriers.
Interesting.
This allows the microchip to read the voltage data without sharing a direct electrical ground with the legal 800-volt system. It protects the low-voltage logic side of the vehicle.
Okay, so that's pathway A, the macro view. What is pathway B?
Pathway B consists of the local management units, the LMUs, which are distributed directly onto the battery modules themselves. They rely on automotive-grade AFE chips chips to read every single individual cell voltage.
Got it.
Then the main microcontroller unit, the MCU, aggregates all those individual readings and computes the sum at a very high frequency.
Now, the crucial term here is asymmetric avoidance. Why is it so imperative that these two systems are mechanically and electrically different? I mean, if you want redundancy, why not just use two identical, highly accurate total voltage sensors?
Because of the profound risk of common cause failure.
And common cause failure.
Yeah. If you use two identical sensors, powered by the exact same low-voltage reference source and routed through the exact same printed circuit board traces, they share identical vulnerabilities.
Oh, I see. So if the 5-volt power supply feeding them both starts to sag due to, like, a failing capacitor, both sensors will output an artificially low reading.
Exactly. They would both be entirely wrong, but perfectly in agreement with each other.
That's terrifying.
Huh?
The system would cross-check them, see a match, and assume everything is fine while the battery is actually entering a critical overcharged state.
It's a perfectly coordinated lie. So to engineer that out of the system, the architecture mandates asymmetric redundancy. The master board's total voltage sensor and the LMU's individual cell sensors must derive their power from completely independent 5-volt reference sources.
They cannot share the same electrical heartbeat.
Right. Furthermore, their physical routing paths on the PCB must be entirely segregated. If a localized surge of heat or electromagnetic interference hits one quadrant of the board, it cannot corrupt the other sensing pathway.
It's like having two independent accounting firms audit a company's financials, but you forbid them from using the same accounting software, they can't work in the same building, and they can't even speak to each other until the final numbers are presented to the board.
That's spot on, and it's the central controller that runs the ultimate lie detector test. This is known as the dynamic cross-verification algorithm.
Okay, walk us through the mechanics of that lie detector. The car is driving down the highway. What is the MCU actually computing to compare these two asymmetric systems?
Every 10 to 20 milliseconds, the battery management system controller executes a continuous mathematical cross-check. It takes the absolute value of the total pack voltage reported by pathway A and subtracts the sum of the individual cell voltages reported by pathway B.
So it's constantly asking, is the macro total diverging from the micro sum? What is the tolerance for that divergence?
Under steady-state conditions, the typical threshold is set between 10 and 15 volts. If the absolute difference exceeds that 10 to 15 volt limit, and it sustains that discrepancy for a set amount of time, what control engineers call the software debounce time, the system officially triggers the P0A03 confirmed fault code.
Okay, here's where it gets really interesting and where I actually see a massive contradiction.
Oh.
Yeah, we established earlier that hard acceleration naturally causes massive physical voltage drops because of all those hundreds of amps rushing through the bus bars and microscopic oxidation layers.
Correct.
So if I hit the gas to pass a truck on the highway, wouldn't that instantly create a transient voltage difference that far exceeds a 15-volt threshold? Wouldn't flooring the accelerator trigger the lie detector and shut my car off right when I'm trying to execute a high-speed pass?
You're touching on the exact engineering paradox that plagues basic BMS designs. If you make the threshold too tight, the car shuts down every time you accelerate.
Right.
But if you make the threshold too wide, you ignore actual dangerous hardware failures. The solution they engineered is a marvel of predictive logic. They integrated the busbar impedance estimation model directly into the control loop.
How does that actually work? Does the software actively calculate the physical mass and resistance of its own copper architecture in real time?
It essentially runs a real-time digital twin simulation of its own high-voltage physical layer. The software is preloaded with a highly detailed dynamic model of the battery's impedance characteristics.
Wow.
It continuously pulls the Hall effect current sensors to measure the exact electrical current being demanded at any given millisecond.
So when you floor the accelerator, the software immediately registers the current spike from, say, 50 amps of cruising load to 400 amps of passing load.
Yes. And before it even runs the cross-verification lie detector, the model instantly computes the expected transient I times R voltage drop that should mathematically occur across those copper bus bars and relays at exactly 400 amps.
So it anticipates the discrepancy before evaluating the error.
It actively compensates for it. It injects a correction factor into the cross-check formula.
How so?
It basically calculates, okay, the total voltage is currently 12 volts lower than the sum of the cells. However, The driver is demanding 400 amps, and my impedance model predicts we should be experiencing exactly 11.8 volts of busbar resistance loss right now.
Ah. Therefore, the residual error is only zero point 0.2 volts. The math balances. Ignore the macro discrepancy.
Exactly.
That is staggeringly complex. The
Mhm.
controller is actively running physical electromechanical simulations of its own copper wiring while simultaneously managing powertrain torque.
It is an absolute necessity. Because if it fails to compensate for that dynamic load, the system defaults to the safe state. And we have to examine what happens when the controller actually confirms a legitimate, unexplainable mismatch.
What happens when the lie detector catches a real hardware failure? The sources detail two completely different safe states depending on the vehicle's operational mode. Let's look at the startup phase first.
Okay.
You get into your EV in the morning, hit the brake, push the start button, and the mismatch is detected immediately during the boot sequence, before you even engage the drive gear.
In that startup scenario, the system categorically refuses to enter the ready state. The vehicle is completely immobilized.
Nice cut of caution.
The rationale for this relates to the physical safety of the high-voltage contactors. When an EV wakes up, it must execute a highly controlled pre-charge phase. It has to slowly saturate the massive capacitors inside the motor inverter, known as the DC link, before it allows the main high-voltage relays to close.
It's like slowly opening a fire hydrant a fraction of an inch to let the downstream pipes pressurize before you yank the main valve fully open, just to prevent a water hammer from blowing the pipes apart.
That is an excellent analogy for electrical inrush current. If the total voltage sensor is throwing a P0A03 mismatch error compared to the cell sensors, the vehicle's central processor is effectively blind.
Right.
It cannot definitively verify the actual voltage potential of the battery, which means it cannot confirm if the DC link capacitors have been safely and equally pressurized.
So what happens if it just guesses? Like if it forcefully closes the main contactor relay
Yeah.
while there is a massive voltage differential between the battery and the empty capacitors.
The resulting inrush surge current would be so unimaginably violent that the physical metal contact pads inside the relay would superheat, melt, and weld themselves permanently together.
Oh, man.
You would instantly create a live, uncontrollable high-voltage system that cannot be shut off. So the BMS protects the vehicle's hardware by refusing to initiate the high-voltage sequence. The contactors just stay open.
Okay, but what if the failure occurs dynamically while the vehicle is already in motion? Let's say you are doing 75 miles an hour on the interstate, and one of those mega-ohm divider resistors we talked about finally degrades from prolonged heat exposure and drifts by 15%.
Right, a real failure at speed.
The dynamic cross-verification algorithm suddenly realizes the total voltage is completely irrational. It can't just instantly sever the high-voltage contactors and lock up the powertrain, right? The loss of power steering and propulsion at 75 miles per hour would be catastrophic.
You've identified the core challenge of functional safety at speed. That is why the driving phase relies on a completely separate protocol called voltage failsafe mode.
How does that work?
If a severe rationality mismatch is confirmed at highway speeds, the primary directive shifts from protecting the hardware to protecting the occupants. The BMS executes a logical override. It essentially declares the total voltage sensor a compromised entity and cuts it completely out of the logic loop.
Wait, it actively ignores a critical safety sensor.
It has to. It switches entirely to relying on the sum of the individual cell data provided by the LMUs to maintain basic operational awareness. Simultaneously, it triggers the malfunction indicator lamp, the MIL, and usually illuminates the power limitation icon on the driver's display.
Often a yellow turtle. The dreaded turtle of doom.
Yeah, the turtle is a very serious warning. The BMS immediately slashes the allowable motor torque by 50%. It coordinates directly with the vehicle control unit, the VCU, to aggressively limit discharge power, effectively forcing the vehicle to decelerate.
Wow.
The engineering goal here is not to continue the journey, but to provide the driver with precisely enough limp home power to safely navigate the vehicle off the active highway lanes and onto a secure shoulder.
It's engineered for graceful degradation. It gives you just enough capability to avoid a collision while essentially flying blind on one of its primary macro sensors.
Exactly.
And then, only after the vehicle has been safely brought to a complete stop and the motor load is reduced to zero, does the system finally drop the contactors and isolate the high voltage pack.
That's right. But, while software compensation models and graceful degradation failsafes are brilliant, they are reactive. They are dealing with a failure that has already occurred.
Sure.
True engineering excellence lies in preventative action. How do we design the physical hardware so these components don't desynchronize, drift, or fail in the first place?
Which brings us to the DFMEA phase design failure mode and effects analysis. This is where engineers attempt to play God with the hardware architecture. They analyze this P0A03 fault. They assign it a severity score of 8 out of 10, meaning it's a critical safety threat with severe operational consequences, and they try to physically engineer the vulnerability out of existence.
Let's address the most glaring systemic vulnerability we uncovered earlier, the 10 to 50 millisecond timestamp latency gap between the total voltage ADC and the sequential polling of the cell AFEs.
The delay that creates the phantom dynamic mismatch.
Right. The countermeasure developed for this is known as the 1 microsecond solution, or global hardware synchronization.
How do you fundamentally alter the data collection architecture to eliminate that latency? You can't just overclock the chips to poll faster.
No, overclocking doesn't solve the sequential nature of the polling. Instead, the engineers redesign the entire communication protocol. Instead of the MCU acting like a teacher taking attendance by asking each cell one by one, they implement a dedicated, hardwired, global broadcast latch pulse.
A broadcast pulse. So it's a single synchronized command sent to every node simultaneously.
Correct. When the central controller determines it needs a clean voltage snapshot, it fires a massive instantaneous electronic pulse across the entire communication bus to every single sensing component on the network. The command is essentially latch.
Meaning, freeze your current analog voltage reading in your local memory buffer right now and hold it until I can collect it.
Yes. And the engineering tolerance here is what is truly staggering. When that pulse propagates across the bus, every single AFE chip on every module, along with the isolated total voltage ADC on the master board, must lock in their physical voltage readings within a synchronized window of exactly 1 microsecond.
1 microsecond, let's really contextualize that. 1/1,000,000th of a second. We talked about a 50 millisecond delay earlier. A microsecond is 50,000 times faster than the latency gap we were dealing with.
It is.
But wait, if you have a massive EV battery pack that is physically 2 meters long, filled with intricate wire harnesses, doesn't the actual propagation speed of the electrical signal through the copper wire become a factor at that timescale?
Oh, absolutely. You're hitting on a deep physical limitation. Electrical signals propagate through copper wire at roughly 2/3 the speed of light. Over a 2-meter battery pack, the signal flight time is roughly 10 nanoseconds.
That's tight.
Add in the propagation delay of the opto-isolators and the clock skew of the microprocessors, and hitting that 1 microsecond synchronization window requires incredibly precise trace length matching on the PCBs and ultra-low latency transceivers.
The engineering overhead just to get everything to take a picture at the exact same time is immense.
It is, but the impact is profound. By forcing every single component to latch its reading within that incredibly tight 1 microsecond window, the timestamp delay is effectively eradicated.
Amazing.
Even if the current is spiking violently at 100 amps per millisecond because the driver just hit a pothole under hard acceleration, the macro total sensor and the microcell sensors are evaluating the exact same microscopic slice of time. The phantom mismatch is engineered out of existence.
That completely solves the temporal problem. But what about the physical vulnerabilities of the circuit boards? We discuss how those precision mega-ohm resistors can suffer from thermal drift and cause rationality errors. How do the engineers physically protect the integrity of the sensing circuits?
Well, the DFMEA outlines 2 major layout principles: spacing and shielding.
Right. In high-voltage PCB layout, the 2 most critical metrics are creepage and clearance. When you are routing 800 volts of raw potential across a fiberglass circuit board, the electricity desperately wants to find a lower potential state. It wants to jump to the low-voltage logic traces or arc to the grounded metal chassis.
Now, clearance is relatively straightforward. It's the shortest distance through the air between 2 conductive points. But what is creepage, and why is it so insidious?
Creepage is the shortest path along the physical surface of the insulating material. If you place a high-voltage trace too close to a ground pin, the intense electrical field can actually ionize the immediate layer of air right at the surface of the PCB.
Okay.
This creates microscopic, localized plasma discharges that slowly carbonize the fiberglass substrate over months and years.
So the high voltage is literally burning its own microscopic conductive track into the insulating board. Exactly. It's called surface tracking. As the carbon track grows, the surface resistance drops. If this occurs near our critical mega-ohm divider resistors, the high voltage essentially creates a parallel parasitic circuit. The sensor reads this leakage current, registers an artificially low voltage, and triggers the P0A03 mismatch.
To combat this, the DFMEA enforces massive physical spacing rules,
Right.
mandating strict creepage distances based on the comparative tracking index of the board material.
And they don't stop at just spacing. They embed protective components directly into the high-voltage sensing pathways. The layout includes specific high-voltage microfuses and high-impedance current-limiting resistors strategically placed in series with the sensing traces.
So if a high-voltage surge does manage to breach the creepage distance or arc across the clearance gap, what happens?
The microfuse instantly ruptures. It sacrifices itself to physically sever the connection before the catastrophic energy can propagate into the low-voltage logic chips. It completely prevents localized arcing from escalating into a thermal runaway event inside the distribution box.
It's a brilliant containment strategy. But there is a massive environmental variable that fundamentally destroys creepage distances, and it's something every car deals with: water.
Yes. And this introduces one of the most fascinating mechanical integrations in the battery pack: breathing without drowning.
Think about the physical realities of an EV battery enclosure. It's an enormous, heavily armored metal tub bolted to the bottom of the vehicle.
Right.
During operation, the thousands of cells generate significant heat. But when you park the vehicle outside overnight in a freezing winter environment, that massive metal mass gets incredibly cold.
The thermodynamics of a sealed volume undergoing extreme temperature fluctuations are entirely predictable.
It creates condensation, it sweats. It's exactly like a runner wearing a non-breathable plastic garbage bag in the winter. Your body heat meets the freezing ambient air against the plastic, and within 10 minutes you are drenched in your own trapped sweat.
Yeah, terrible feeling.
If an EV battery enclosure is hermetically sealed like a submarine, those thermal cycles will physically force the humidity suspended in the trapped air to condense into liquid water droplets on the inner surfaces.
And consider what happens when a microscopic droplet of liquid water forms directly across the surface of the PCB, bridging the gap between those precision mega-ohm divider resistors we meticulously spaced apart.
Oh man, the water droplet completely bypasses the engineered creepage distance. The water acts as a highly conductive bridge. The high voltage potential surges across the water, the resistance of the circuit plummets, the ADC misreads the voltage, and you instantly trigger a P0A03 fault simply because the battery enclosure experienced a temperature swing.
Therefore, the mechanical engineers cannot hermetically seal the enclosure. They have to allow the internal volume to breathe to equalize pressure and vent humidity.
But how do you let a metal tub strapped to the bottom of a car breathe without allowing liquid water from a deep puddle to flood the battery?
They integrate a Gore valve. Now, if you are familiar with high-end outdoor gear, you know the brand Gore-Tex. The technology relies on a microporous fluoromembrane, often expanded polytetrafluoroethylene, or EPTFE.
Right.
The physical architecture of this membrane is extraordinary. The pores in the material are engineered to be roughly 700 times larger than a water vapor molecule, but 20,000 times smaller than a liquid water droplet.
It is an elegant application of material science solving an electrical vulnerability. By integrating these waterproof, breathable Gore valves into the structure of the battery casing, the enclosure can continuously equalize its internal vapor pressure with the outside atmosphere. It effectively exhales the internal humidity before it can condense.
The sensitive high-voltage electronics remain bone dry, completely immune to the condensation phenomenon that would otherwise compromise the macro-voltage sensors.
So on a digital CAD model, the system is flawless. We have 1 microsecond synchronized latches overcoming the speed of light, massive creepage distances protected by sacrificial microfuses, and advanced fluoromembranes managing the thermodynamics of the enclosure.
But the real world is infinitely messier than a CAD model.
Yep. You can engineer the perfect theoretical architecture, but if a single line worker on the assembly floor under-tightens a critical bus bar bolt by a quarter of a turn, the physical clamping force drops.
Right.
The dynamic resistance spikes under load, the phantom voltage drop returns, and the entire multi-million-dollar vehicle architecture is compromised.
Which perfectly navigates us into the realities of mass production. This is the PFMEA process failure mode and effects analysis. How do manufacturers exert absolute control over the chaotic variables of building tens of thousands of highly volatile battery packs?
In automotive manufacturing, process engineers obsess over the 5M1E variables. That stands for man, machine, material, method, measurement, and environment. When you are assembling an ASIL-D critical high-voltage system, you absolutely cannot rely on the man variable to simply perform flawlessly every single time.
You really can't. Human operators experience fatigue, distraction, and repetitive strain. The process must rely heavily on machine and measurement to physically enforce the method.
Let's examine the first critical process control, the smart wrenches. We established in the root cause analysis that insufficient clamping force on the copper busbar bolts induces massive dynamic voltage drops. How do manufacturers guarantee that every single bolt across thousands of battery packs is perfectly secured?
They completely eliminate standard pneumatic or manual torque wrenches from the high-voltage assembly lines. They transition to 100% adoption of smart electric servo tightening systems.
Oh, wow.
These aren't just drills. They're incredibly sophisticated robotic manipulators that utilize a torque angle dual parameter dynamic closed-loop control system.
Let's break down why simple torque is inadequate for an ASIL-D connection. Torque is merely a measurement of twisting force, right?
Right. If a technician uses a standard torque wrench to tighten a bolt, and a tiny burr of metal or a grain of dirt is caught in the threads, the wrench will encounter significant mechanical resistance.
The wrench registers that resistance, assumes the bolt is fully seated, and clicks. It says, "I have achieved my target torque of 9 Newton meters." But the reality is that the bolt is merely jammed on the debris. The thick copper busbar plates underneath the bolt head aren't actually compressed tightly together.
Precisely. The static torque measurement is lying about the actual clamping force. To overcome this, process engineers introduced the angle parameter. The smart servo system doesn't just measure the resistance. Its internal encoders physically track the degrees of rotation of the bolt head during the fastening cycle.
The manufacturing specifications for these connections are incredibly rigid. The process targets exactly 9.0 plus or minus 0.5 Newton meters of torque, while simultaneously demanding an angle rotation tolerance of between 30 degrees and 45 degrees.
Consider the logic of that dual parameter check. The servo controller dictates, I must encounter exactly 9 Newton meters of twisting resistance, and D, the bolt, must physically rotate between 30 and 45 degrees during the final seating phase to properly stretch the shank of the bolt and achieve the exact elastic yield limit required for optimal clamping force.
If the torque hits 9 Newton meters, but the encoder registers that the bolt only rotated 10 degrees, the controller instantly knows the threads are jammed or cross-threaded, the clamping force is compromised.
And the integration goes even further. These smart wrenches are networked directly into the facility's manufacturing execution system, the MES. Before the operator even engages the tool, they must scan the barcode of the specific battery module.
The system is tracking everything.
It is. The MES knows exactly which sequence of bolts is being addressed. If the dual parameter dynamic check registers a failure, if it hits 9.6 Newton meters or 46 degrees of rotation, the entire assembly line physically halts.
The conveyor belt literally stops moving.
Yep.
The MES locks out the tool. A quality assurance supervisor must physically intervene, evaluate the compromised joint, replace the hardware if necessary, and clear the fault code in the system before production can resume.
It is an aggressive, automated interlock against human error. But even with robotic tightening, the physical condition of the mating surfaces must be prepared. You can't just bolt dirty copper together.
Definitely not.
Yeah.
The process mandates that prior to assembly, the copper busbar contact zones undergo aggressive mechanical polishing to remove any microscopic oxidation layers. Following that, a specialized conductive antioxidation paste is applied.
It functions very similarly to thermal paste used between a computer processor and a heatsink, but it's engineered for electrical conductivity. It fills in the microscopic imperfections and valleys in the machined copper surface to maximize the actual contact area and minimize the initial parasitic resistance. And as a final analog failsafe, after the smart wrench registers a perfect cycle, the operator uses a specific high-visibility paint pen to draw a torque seal check line continuously across the bolt head and onto the adjacent copper plate.
Oh, I've seen those. It serves as a visual tamper-evident seal.
Right. If that specific bolt ever experiences severe vibration and backs out by even a fraction of a millimeter over the lifespan of the vehicle, that solid paint line will fracture and misalign. A diagnostic technician examining the pack 5 years later can instantly identify the compromised connection without needing to retorque every bolt.
That controls the macro hardware, the massive copper bars. But what about the micro hardware? The complex printed circuit boards that run the 1 microsecond latches and hold the mega-ohm resistors. The manufacturing tolerances there are microscopic.
The quality control on the PCB assembly line relies heavily on advanced optics and machine learning. The standard mandates 100% adoption of 3D SPI solder paste inspection and 3D AOI automated optical inspection.
Walk us through the 3D SPI process. Before any microchips or resistors are even placed on the bare circuit board, a machine forces a precise amount of gray solder paste through a metal stencil onto the contact pads.
Immediately after the stencil is removed, a high-precision 3D laser interferometer sweeps across the board. It maps the exact microscopic volume, height, and area of every single deposit of solder paste.
Why is the exact volume so critical?
Well, if the stencil was slightly clogged and only deposited 85% of the required paste volume, the resulting physical connection after baking will lack the necessary structural integrity.
Makes sense.
It leads to what is known as a cold solder joint, a connection that appears visually intact but lacks sufficient metallic bonding to conduct current properly without introducing massive resistance or eventually failing under thermal stress. The 3D SPI rejects the board before a single component is wasted on it.
And the automated optical inspection?
After the components are placed by the pick-and-place robots and the board travels through the high-temperature reflow oven to melt the solder, it enters the 3D AOI machine. This system utilizes a high-resolution multi-angle camera array paired with machine learning algorithms to analyze the precise X, Y, and Z spatial orientation of every single component.
Think back to our discussion on creepage and clearance distances during the DFMEA phase. If one of those critical mega-ohm divider resistors happens to float on the liquid solder during the baking process and shifts its position by just half a millimeter, it might now reside dangerously close to a low-voltage ground pin.
Exactly. And the 3D AOI system detects that microscopic spatial deviation. It recognizes that the engineered creepage distance has been compromised during manufacturing, and it automatically flags the board to be scrapped or reworked. It guarantees the physical geometry of the safety systems.
It's an incredible level of microscopic scrutiny. But there is another advanced process mentioned in the sources designed to combat a specific, terrifying chemical failure mode. They use vacuum conformal coating. What exactly does that entail?
We discussed how the Gore valve manages the macro humidity of the enclosure. But engineers demand a secondary, localized layer of defense directly on the PCB. They apply a conformal coating, a highly durable, electrically insulating polymer resin, over the entire populated circuit board.
It's essentially encapsulating the entire board in a layer of liquid plastic that hardens into a permanent shell. But the critical detail is that they perform this application inside an automated high-density vacuum chamber. Why go through the massive expense of pumping the air out? Why not simply spray the resin on the assembly line?
Because if you apply a viscous resin in open atmospheric pressure, microscopic air bubbles are inevitably trapped underneath the flat bodies of the microchips and between the densely packed metal pins.
Oh, I see.
If ambient moisture eventually permeates the polymer coating over years of operation and accumulates within those trapped air voids, you create the optimal microenvironment for a devastating phenomenon known as electrochemical migration, or ECM.
Electrochemical migration. Break down the chemistry of that failure mode for us.
ECM is the literal physical growth of conductive metal where none should exist. If you have three conditions: trapped moisture, an applied voltage bias between two adjacent pins, and a tiny air gap, the electrical field will literally strip metal ions off the positive pin, float them through the microscopic layer of moisture, and deposit them onto the negative pin.
So the electrical field is physically tearing the metal apart at an atomic level and reassembling it across the gap.
Over months of continuous operation, this ion transfer grows a tiny microscopic metal bridge, referred to as a dendrite, reaching from one pin to the other.
It is literally building its own wire to short itself out.
Exactly. The metal walks across the gap until it makes contact, creating a hard short circuit that completely destroys the sensing logic. By executing the conformal coating process in a pure vacuum, the pressure differential forcefully extracts every single molecule of trapped air from underneath the components before the resin polymerizes and hardens.
Zero air gaps means zero localized moisture accumulation, which means zero possibility of electrochemical migration. The vulnerable pins are permanently entombed in a flawless, homogeneous layer of insulation.
It is an obsessive level of process control. But before the completed battery pack is allowed to leave the manufacturing facility, it must undergo one final individualized validation step: the end-of-line calibration.
This is where they reconcile the physical hardware with the software. Even with 3D laser inspections and vacuum chambers, every single battery pack is inherently unique. The millions of microscopic resistors and capacitors all have tiny, acceptable manufacturing variances. So before the pack is cleared for shipping, it's connected to a massive automated calibration rig.
The calibration rig injects highly precise laboratory-grade voltage steps into the battery pack. It essentially commands, I am currently applying exactly 400,000 volts to your terminals. It then queries the vehicle's total voltage sensor via the communication bus. What value are you reading?
The vehicle's internal sensor might respond, I am registering 399.985 volts.
The automated system calculates that minute discrepancy. It then alters the ambient temperature of the testing environment and repeats the process to analyze how the specific sensor hardware reacts to thermal changes. It uses this data matrix to calculate a highly specific temperature drift slope unique to that exact physical battery pack.
It's mapping the precise personality flaws and inaccuracies of that specific hardware assembly.
Precisely. It generates a set of customized calibration coefficients and permanently burns them into the non-volatile flash memory of the battery management system. From that moment forward, the software logic understands my physical sensor hardware consistently reads marginally low when the ambient temperature exceeds 40 degrees Celsius, so I will proactively apply mathematical correction factor before I execute the dynamic cross-verification algorithm.
So if we review the journey so far, the engineers designed an impeccable theoretical architecture featuring 1 microsecond latches and Gore-Tex breathing valves. The manufacturing division executed the design flawlessly, using smart robotic wrenches, vacuum-sealed resins, and individualized thermal calibration. It seems like the engineering challenge is solved. The system is perfect.
In theory, yes, but in the realm of functional safety, theory is irrelevant. You do not achieve an ASIL-D rating by simply assuming your designs and factories work. You have to unequivocally prove that the architecture survives the brutal realities of the physical world.
And that reality check brings us to the fifth and final dimension, the DVP&R Design Verification Plan and Report. This is the mass production validation phase. It's the absolute torture chamber.
The validation protocols are designed to aggressively attack every single vulnerability we've discussed. Let's start with the hardware in the loop, or HIL, step current test. This specific protocol is engineered to validate the efficacy of the software compensation, the busbar impedance estimation model that dynamically ignores voltage drops during acceleration.
How do you practically test that compensation logic on a laboratory bench?
You connect the battery management system controller to a massive high-power simulation rig. And here is where the validation engineers get incredibly devious. They intentionally sabotage the physical hardware. They take the main high-voltage power loop and purposefully splice a microscopic 0.5 million precision.
They are mimicking the exact parasitic resistance of a worker under-tightening a bus bar bolt or a severely oxidized connection joint. They are intentionally giving the system a physical disease to see how the immune system reacts.
Exactly. With the compromised hardware in place, they subject the battery pack to violent transient step currents. They instantly swing the applied load from negative 200 amps, simulating maximum regenerative braking, straight to positive 200 amps, simulating maximum acceleration. They execute this 400 amp swing in milliseconds.
That is an incredibly violent electrical stress test. What specific metrics is the validation system monitoring to determine a pass or fail?
The acceptance criteria demand absolute mathematical perfection. The software model must instantly recognize the massive current spike, accurately calculate the resultant dynamic voltage drop across that sabotaged 0.5 milliohm resistor, and actively mathematically compensate for it in real time.
Okay.
The strict requirement dictates that the dynamic residual error, the absolute difference between the total macro voltage and the sum of the microcell voltages after the software applies its compensation factor, must be rigidly maintained at less than or equal to plus or minus 1.0 volt.
Plus or minus 1 volt of error across an entire 400 volt or 800 volt battery architecture while violently swinging 400 amps of current across an intentionally diseased connection. That's insane.
And it must maintain that tolerance continuously. If the residual error briefly spikes to 1.1 volts during the transition, the software model fails validation. The system must categorically guarantee that absolutely no false P0A03 mismatch alarms are ever triggered under extreme dynamic duress. The mathematics must remain robust regardless of the physical load.
Okay, that definitively proves the software compensation logic works under fire. What about the global hardware synchronization? The 1 microsecond latch command that eliminates the timestamp delay. How do you physically prove that the signal propagates across the entire board in under a millionth of a second?
They execute the 1 microsecond sync test. And they do it by subjecting the entire communication architecture to a massive electromagnetic assault. They utilize specialized injection probes to hit the system with an aggressive rate of current change, a DID of greater than or equal to 100 amps per millisecond.
That is essentially a localized electromagnetic shockwave.
It creates immense electromagnetic interference EMI across the printed circuit boards. The explicit goal is to attempt to overwhelm the low-voltage communication transceivers, induce signal jitter, and force a delay in the latch command.
They are trying to jam the radar.
Precisely. During the CMI assault, validation engineers connect ultra-high-speed differential oscilloscope probes directly to the physical communication lines at the furthest extremes of the battery pack. When the central controller broadcasts the latch command, the physical propagation delay between the master board and the most remote AFE chip must strictly remain less than or equal to 1 microsecond, despite the overwhelming interference.
And what is the acceptable impact on the actual voltage reading?
The transient voltage ripple induced by any microscopic timing variance or signal degradation must remain below 1.5 volts. The localized sensors must capture the perfect, synchronized snapshot even while the surrounding electrical environment is incredibly hostile.
It's an incredible feat of signal integrity. But let's shift from electrical torture to environmental torture. We discussed the vacuum-sealed conformal coating designed to prevent electrochemical migration. How do they prove that thin layer of polymer actually stops metal dendrites from growing? Welcome to environmental hell.
The environmental validation protocols are where physical chemistry meets endurance testing. The validation engineers take these fully populated, vacuum-coated, perfectly manufactured printed circuit boards, and they intentionally contaminate them. They drop actual liquid ethylene glycol standard automotive engine coolant directly onto the high-voltage component pins.
They are physically spilling highly conductive corrosive chemicals directly onto the safety sensors.
Yes, they are simulating a catastrophic failure of the battery's internal liquid thermal management system. Once contaminated, the board is locked inside a dual 85 environmental test chamber.
Dual 85. I assume that relates to the atmospheric conditions.
It means the chamber is continuously maintained at 85 degrees Celsius, which is roughly 185 degrees Fahrenheit, and an oppressive 95% relative humidity. It simulates the absolute worst-case scenario, a boiling, dripping, chemically saturated microclimate.
How long does a board remain in the chamber? A standard 24-hour cycle.
500 continuous hours.
Over 20 days straight, inside a boiling 95% humidity, chemically soaked oven. That is unimaginably brutal.
And it gets worse. While the board is baking in the chamber, they actively apply a constant 5-volt direct current bias across the critical sensor pins. They are actively trying to catalyze the electrochemical migration process we discussed earlier. They are desperately trying to force the metal ions to migrate through the coating and grow those catastrophic dendrite bridges.
What are the specific metrics required to pass after 500 hours of continuous chemical and thermal torture?
Upon removal from the chamber, the board is subjected to intense analysis. First, the foundational insulation resistance of the PCB substrate must remain strictly greater than or equal to 500 megaohms. Second, the active leakage current across the high-voltage traces must be less than 1.0 milliamp. Finally, and most critically, the board is examined under high-power electron microscopes. There must be absolutely zero visual or structural evidence of metal dendrite growth.
The vacuum-sealed polymer resin must hold flawlessly against heat, humidity, chemicals, and electrical bias. If a single microscopic wire of displaced metal has grown across a gap, the entire material selection and manufacturing process fails.
It proves the physical design can survive a localized apocalypse. But the final series of DVP&R tests, detailed in the methodology, shifts the focus from the design of the board to the integrity of the factory floor itself. This is about catching the bad apples. The manufacturers have to conclusively prove that all those advanced robotic tools and laser scanners actually intercept real-world assembly errors.
Right. It's one thing to boast about a highly automated quality control process. It's an entirely different challenge to prove your automated systems actually recognize a critical failure when it occurs on the line.
Yeah.
How do you test the factory?
The validation engineers execute a campaign of intentional industrial sabotage. They purposefully construct defective battery packs and secretly inject them onto the active assembly line to see if the systems catch them.
It's essentially a penetration test, but for heavy manufacturing.
Exactly. They organize 3 distinct test groups. Group A is the baseline control, the perfect golden pack. Every bolt is secured with the smart wrenches, perfect torque angle compliance, 0 defects. Then they introduce Group B, For this group, they bypass the robotic smart wrenches entirely. Technicians use standard pneumatic tools to intentionally leave the main high-voltage busbar bolts exactly 20% below the specified torque value.
They are leaving the bolts just loose enough to introduce severe dynamic resistance, but tight enough that they appear perfectly seated to a visual inspection.
Then they construct Group C. They take the raw copper bus bars and subject them to a chemical bath to intentionally induce a medium-grade layer of surface oxidation. They then bolt these diseased copper plates together using the correct smart wrenches, achieving the perfect torque and angle specifications.
So for Group C, the robotic assembly data looks flawless, the clamping force is correct, but the foundational metallurgy of the connection is fundamentally compromised.
All three groups are anonymously routed down the production line to the final end-of-line, or EOL, test station. As the packs initiate their boot sequence, the EOL testing rig fires a massive, localized step current pulse load through the architecture.
And the pass criteria. The automated EOL system has to successfully differentiate the sabotaged packs from the golden pack based purely on the transient electrical response.
The requirement is absolute. The automated EOL system must 100% intercept every single pack from Group B and Group C. It must accurately sense the microscopic variations in dynamic resistance during that massive pulse, identify the compromised packs, immediately lock them out of the functional state, and permanently bind the failure data to the pack's serial barcode so they can never be shipped to a vehicle assembly plant.
It has to definitively catch every single bad apple, regardless of whether the failure was mechanical looseness or chemical oxidation.
And the statistical analysis goes even deeper. The raw operational data generated by the robotic smart wrenches over thousands of cycles is analyzed. Process engineers calculate the Process Capability Index, known as CPK. The requirement is that the CPK of the robotic tightening tools must remain strictly greater than or equal to 1.67.
What does a CPK of 1.67 actually signify in a manufacturing context?
It mathematically guarantees that the manufacturing process is so tightly controlled and the distribution of torque variations is so incredibly narrow that the physical probability of the machine accidentally producing a bolt outside the specified tolerance limits is roughly 1 in a million. It proves the machines are statistically incapable of making a mistake under normal operating conditions.
Okay, there's one final brutal validation test detailed in the methodology, the high-pot test. High potential testing. This sounds like the ultimate stress test of the physical insulation.
It is the absolute final verification of physical safety and containment. They take the fully assembled, fully sealed battery pack and they hit the architecture with 2,500 volts of direct current.
2,500 volts. That is immense. The entire vehicle architecture is only designed to operate at 400 or perhaps 800 volts.
Exactly. They hit the system with massive, intentional overvoltage, and they hold that extreme potential continuously for 60 straight seconds. They are deliberately attempting to force the electricity to break through the internal insulation, jump across the engineered creepage gaps, overwhelm the microfuses, and arc violently to the grounded metal chassis of the vehicle.
What does the pack have to do to pass?
The total leakage current escaping to the chassis must remain strictly under 1.0 milliamp. There can be absolutely no audible arcing, no visual flashing, and no dielectric breakdown of the insulating materials. The battery architecture must swallow 2,500 volts of raw power for a full minute and remain perfectly safely sealed.
If we pull back and connect all of this to the bigger picture, the sheer scale of the engineering effort required to mitigate a single rationality fault code is breathtaking.
When you look at the totality of these dimensions, the 500-hour chemical boiling, the CPK statistical modeling of robotic wrenches, the 1 microsecond electromagnetic latches, the vacuum-sealed resins, what you are really analyzing is the design of an artificial immune system. These tests are not merely about identifying broken parts. They are about conclusively proving that the system's immune response is flawless. The vehicle must be capable of recognizing a localized failure, logically isolating it, compensating for the physical reality, and protecting the host at all costs.
We have covered an incredible expanse of technical ground today. Let's briefly retrace the path we've taken. We started by examining a frustrating restaurant bill, which led us into the physical pathology of high-current parasitic drops, tracking down multi-volt dynamic errors, hiding in oxidized, under-tightened copper bolts, and uncovering phantom mismatches caused by 50-millisecond delays in sequential polling.
We then explored how the vehicle's architecture fights back, using dual-independent asymmetric sampling to prevent common cause failures, and how it deploys real-time busbar impedance estimation models to mathematically ignore dynamic voltage drops when you aggressively dramatically accelerate, yet gracefully degrades to a limited power turtle mode if a mega-ohm resistor inevitably drifts from thermal degradation.
We moved upstream to see how engineers aggressively play God with the hardware during the DFMEA phase, deploying 1 microsecond global broadcast pulses to beat signal latency, enforcing strict physical creepage distances protected by sacrificial microfuses, and integrating advanced Gore-Tex fluoromembranes to allow the massive enclosure to breathe without drowning its own circuits in condensation.
From there, we entered the manufacturing floor, detailing the PFMEA controls. Robotic torque angle smart wrenches that physically halt the assembly line if they miss a degree of rotation, 3D laser interferometry verifying microscopic volumes of solder paste, and vacuum chambers entombing the entire PCB in a void-free polymer resin to eradicate electrochemical migration.
And finally, the ultimate crucible, the DVPNR validation. Intentionally sabotaging circuits with 0.5 million resistors, boiling them in engine coolant and 95% humidity for 20 straight days, slipping compromised packs onto the assembly line to test the automated end-of-line intercept systems, and slamming the final, fully assembled architecture with 2,500 volts of pure power just to mathematically prove the insulation will not yield.
It is a relentless, invisible war of precision. And it is the exact reason why modern high-voltage architectures can be considered genuinely safe and reliable under extreme highway conditions.
It fundamentally changes how you perceive the simple act of pressing the start button and merging onto the highway. But before we wrap up this deep dive, the methodology leaves us with one final, deeply provocative engineering challenge to consider. It's an interaction that builds upon the absolute limits of everything we just analyzed.
Now that you comprehend the obsessive microsecond-level precision required to accurately calculate the total pack voltage, consider this scenario. When the vehicle first wakes up from a deep sleep state, how does this incredibly precise hardware synchronization interact with the downstream safety shutdown logic? Specifically, the critical safety check known as 502 P0A01 high-voltage contactor welding during the highly volatile pre-charge phase.
Right, the check that verifies the massive power switches haven't melted themselves permanently closed.
Exactly. If the hardware voltage mismatch timing is off by even a fraction of a millisecond during that hypersensitive dynamic wake-up sequence, could the central controller accidentally interpret a perfectly normal startup transient as a catastrophic hardware failure? And if it makes that irrational deduction, could it preemptively trigger a massive safety shutdown that ironically damages the very contactors it's trying to protect? Does the ultra-fast artificial immune system ever accidentally turn on the body it was designed to save?
That is an incredible paradox to leave off on. The delicate razor-edge balance between engineering ultra-fast safety interventions and inadvertently causing unintended self-destruction through oversensitivity. I want you to mull that over the next time you hear the subtle click of the high-voltage contactors engaging in your garage. And the next time a waiter drops a restaurant bill with a math error on your table. Just be glad you don't have to cross-check the discrepancy in under 1 microsecond while 400 amps of lethal current surge through the silverware. Thank you for joining us on this deep dive into the complex world of modern engineering. We'll be back to unpack more invisible systems soon.